Hi guys, welcome back to engineeringtalks.com. This is the best way to greet anyone, especially these days. This would be the best option. You know why? Social distancing. So maintain social distancing whenever you go out and take all the precautionary measures and follow all the guidelines. We'll overcome this together. So let's get into the topic. In today's class, we'll go through inverse Laplace transforms, especially the introduction part. And then we'll see the method of partial fractions. And finally, we'll find out the inverse Laplace transform of a function using this method. So happy learning. We'll be dealing with the topics inverse Laplace transforms and method of partial fractions. First, let's go through the introduction of inverse Laplace transforms. Laplace of f of t equal to f of s. We all know that. So, f of t will be equal to Laplace inverse of f of s. That is, we just take this L to the RHS so that we get Laplace inverse. So Laplace inverse of f of s will be equal to f of t. And this function f of t is known as the inverse Laplace transform of the given function f of s. For example, Laplace inverse of 1 by s minus a is given by e raised to at, and Laplace inverse of 1 by s plus a is given by e raised to minus at. How? We know the Laplace transforms of e raised to at is 1 by s minus a, and Laplace of e raised to minus at is given by 1 by s plus a. So just take this L to the RHS. We'll get e raised to at equal to 1 by s minus a and e raised to minus at equal to 1 by s plus a. Now let's move on to the properties. First, the linearity property. Linearity property of inverse Laplace transforms. If a and b are any constants and f of s and g of s are functions of s, then we'll have Laplace inverse of a f of s plus b g of s is equal to, we can split these two terms, that is a Laplace inverse of f of s plus b Laplace inverse of g of s. Because a and b are constants, we can take that outside. So it will be a Laplace inverse of f of s plus b Laplace inverse of g of s, which will give you a f of t plus b g of t. Property is first shifting property. Let's see what this is. Laplace inverse of f of s plus a is equal to e raised to minus at Laplace inverse of f of s, which is equal to e raised to minus at f of t. We already saw the first shifting property of Laplace transforms. So please go and watch those videos before watching this video, because those are the basics. Now let's see how we got this from this. See here, we have f of s plus a. What was the reason this f of s got converted to f of s plus a? The reason was e raised to minus at. Because Laplace of e raised to minus at f of t is f of s plus a. So if we take this e raised to minus at, which is the reason for f of s to get converted into f of s plus a, we can get the original f of s back. So e raised to minus at Laplace inverse of f of s, which is equal to e raised to minus at f of t. F of t because Laplace inverse of f of s is f of t. Now we'll have a proof for this. Laplace of f of t is equal to f of s. We all know that. And Laplace of e raised to minus at f of t is given by f of s plus a according to the first shifting property of Laplace transforms. So when we take this L to the RHS, we'll have Laplace inverse of f of s plus a is equal to e raised to minus at f of t. Now let's do some problems based on this. F of s is given by s by s square plus 36, which is equal to s by s square plus 6 square. That is, we can write 36 as 6 square, right? Now this is of the form s by s square plus a square. We all know that Laplace of sin 80 is given by a by s square plus a square, and Laplace of cos AT is given by s by s square plus a square. Now this s by s square plus 6 square is of the form s by s square plus a square, which is the Laplace of cos AT. And here a is 6. So Laplace inverse of s by s square plus a square is equal to Laplace inverse of s by s square plus 6 square, which is equal to cos AT, which is equal to cos 6t. The next question, f of s is equal to 2 pi by s minus pi. We have to find out the Laplace inverse for this function. So Laplace inverse of e raised to at is given by 1 by s minus a. Look at this. This is of the format 1 by s minus a. This 2 pi is a constant, so we don't have to bother about that. We can take that outside. So 2 pi Laplace inverse of 1 by s minus pi. This pi is equal to a, that is pi is in the place of a. 1 by Laplace inverse of 1 by s minus a is given by e raised to at. So Laplace inverse of 1 by s minus pi is given by e raised to pi t, and we'll write this 2 pi as it is. 2 pi is a constant, so we have taken this outside. 2 pi Laplace inverse of 1 by s minus pi is equal to 2 pi e raised to pi t. These are the inverse Laplace transforms of the elementary functions. Please do by heart it. So first one is Laplace inverse of 1 by s, which is given by 1, because Laplace of 1 is 1 by s. So Laplace inverse of 1 by s will be 1. Similarly, Laplace inverse of n factorial by s raised to n factorial is given by t raised to n, because Laplace of t raised to n is n factorial by s raised to n plus 1. Now we can write Laplace inverse of 1 by s raised to n plus 1 is equal to t raised to n by n factorial. We just took this n factorial from LHS to RHS. We can also rewrite it as Laplace inverse of 1 by s raised to n is equal to t raised to n minus 1 by n minus 1 factorial. Similarly, Laplace inverse of 1 by s plus a is equal to e raised to minus at, and Laplace inverse of 1 by s minus a is e raised to at. Laplace inverse of 1 by s minus a raised to n. Okay, now we know that Laplace inverse of 1 by s raised to n is t raised to n minus 1 by n minus 1 factorial. Now you see here, instead of s, it is s minus a. This s minus a, s got converted to s minus a because of this, that is e raised to at. If it was s plus a in the place of s minus a here, we would have written e raised to minus at in the place of e raised to at. So Laplace inverse of 1 by s minus a raised to n is equal to e raised to at Laplace inverse of 1 by s raised to n, which is equal to e raised to at t raised to n minus 1 by n minus 1 factorial. Now Laplace inverse of a by s square plus a square is equal to sin at. Laplace inverse of s by a square plus a square is equal to cos at. Similarly, Laplace inverse of a by s square minus a square equal to sin h at. Laplace inverse of s by a square minus a square is equal to cos h at. Laplace inverse of b by s minus a the whole square plus b square is equal to e raised to at sin bt, e raised to at because s got converted to s minus a. So when we take this e raised to at outside, it becomes Laplace inverse of b by s square plus b square. So b by s square plus b square is the Laplace of sin bt. So Laplace inverse of b by s square plus b square becomes equal to sin bt. Now Laplace inverse of b by s minus a the whole square minus b square is equal to e raised to at sin h bt. Similarly, Laplace inverse of s minus a by s minus a the whole square plus b square equal to e raised to at cos bt, and Laplace inverse of s minus a by s minus a the whole square minus b square is equal to e raised to at cos h bt. Method of partial fractions. Laplace transform of a function f of t usually yields a rational algebraic function, right? The whole purpose of doing this Laplace transformation is to convert differential equations into simple algebraic equations or algebraic functions. So, before finding out the inverse Laplace transform of such a rational algebraic function, we'll have to express it first in the form of partial fractions. So, how can we resolve a function into partial fractions? The denominators of algebraic functions may have non-repeated or repeated linear or quadratic factors. So, depending upon whether the denominator consists of non-repeated linear or non-repeated quadratic or repeated linear or repeated quadratic factor, we'll have separate cases for finding out the partial fractions. So, let's see the first case. If we have a non-repeated linear factor s minus a in the denominator, then it corresponds to a partial fraction of the form a by s minus a, where a is a constant. Now, if we have a repeated linear factor like s minus a raised to r in the denominator, then it corresponds to sum of r partial fractions of the form a1 by s minus a plus a2 by s minus a square plus a3 by s minus a cube plus up to ar by s minus a raised to r. Now, what if we have a non-repeated quadratic factor like s square plus as plus b in the denominator? Then the partial fraction corresponds to the form as plus b by s square plus as plus b, or a1s plus a2 by s square plus as plus b. This a, b, a1, a2, all these are constants. Now, if we have a repeated quadratic factor like s square plus as plus b raised to r in the denominator, then the partial fraction takes the form a1s plus b1 by s square plus as plus b plus a2s plus b2 by s square plus as plus b the whole square plus etc. plus ar s plus br by s square plus as plus b raised to r. After splitting the function into partial fractions, we'll have to determine the unknown constants a, a1, b1, a2, etc. So for this, after having found out the partial fractions corresponding to the factors in the denominator, what we'll have to do is that we have to make the denominator same on both sides of the equation, and then equate the constants and equate the coefficients of powers of s on both sides of the equation, and finally we get the values of a, a1, b1, b2, etc. And after finding out the values of these unknown constants, we can get the inverse Laplace transform of the function. The inverse Laplace transform of the function 1 by s square plus s. F of s is equal to 1 by s square plus s, which is equal to 1 by s into s plus 1, right? Now, we have to split this function into partial fractions. Let's see how we can split this function into partial fractions. Now, this function consists of 1 by s and 1 by s plus 1. In 1 by s, in the denominator, we have a non-repeated linear factor s. So, we will get the partial fraction as a by s. In the case of 1 by s plus 1 also, we have a non-repeated linear factor in the denominator, that is s plus 1. So, we can write it as b by s plus 1. Now, we have to make the denominators on both sides of the equation equal. So, for that what we can do, we can cross multiply and write it as a into s plus 1 plus bs by s into s plus 1. So, we will get 1 equal to s plus a plus bs. Denominators are the same. So, we need not write the denominators on both sides of the equation. Now we have to equate the constants. We'll get 1 equal to a. So we got the value of the unknown constant a. Now we'll equate the coefficients of s. That is, left side we have 0. We don't have any s terms. So it is 0 equal to a plus b. Now we already know the value of a. So b plus 1 is equal to 0. Therefore b is equal to minus 1. We will substitute the values of the constants a and b in the equation. So we will get 1 by s into s plus 1 is equal to 1 by s minus 1 by s plus 1. Now we will take the Laplace inverse Laplace transform of 1 by s into s plus 1, which is equal to Laplace inverse of 1 by s minus 1 by s plus 1. Using linearity property, we can split these two terms. Laplace inverse of 1 by s minus Laplace inverse of 1 by s plus 1, which is equal to 1 minus e raised to minus t, because Laplace inverse of 1 by s is 1 and Laplace inverse of 1 by s plus 1 is e raised to minus t. So guys, please do like, share and subscribe my channel, and don't forget to press the bell icon. Thank you.